Today we want to look at the kinematics of a particle moving in a circle. We want to measure the centripetal acceleration versus its angular velocity for a particle moving in a circle. We're going to use the circuit board, the Bluetooth sensor board with its IMU, inertial measurement unit, to measure the centripetal acceleration and the angular velocity. If you're looking at this video without having the document here in front of you, stop the video now and grab a copy of that handout, Centripetal Acceleration versus Angular Velocity using Sphero Mini Sensor Board. This document gives you a step-by-step procedure that you can follow to build the device, to take the data and analyze it using Excel. Everything you need is in the at-home kit that you got from Furman P2P. You need the sensor boards, the little plastic cups. I said 8 quarters. You just need $1 worth of quarters for the counterweights. A couple of lengths of twine and the little cardboard mini centrifuge piece that you also got in that home kit package. You need that and some Scotch tape. So let's look at circular motion going all the way back to the early days of the course. So if you have a particle that's moving in a circle, if it has a radius r and sitting here with a tangential velocity that looks like that, if this is the v tangential, then you recall that there's a radial acceleration, a radial, which has the value of a tangential is a radial is v tangential squared over the radius. That's in terms of the tangential velocity and the radius. You're going to learn in chapter 10 that there's another way to talk about circular motion in terms of the angular velocity. Omega is the angular velocity of this particle. It's 2 pi over the period of the oscillation. It's how many degrees per second? No, it's how many radians per second this particle goes around. So it's angular velocity. I can't talk and write at the same time. So if you look ahead to chapter 10, you're going to learn that v tangential is r times omega. So if I put this value for v tangential into the expression for the radial acceleration, that's r times omega quantity squared over r, so that's r squared times omega squared over r. This r cancels one of those up there, so the radial acceleration is r times omega squared. 2 different equations for the radial acceleration. 2 different equations, one in terms of, both in terms of the radius, this one in terms of the tangential linear velocity, this in terms of the angular velocity. They have the same meaning. Huh? This one looks like it goes 1 over r. It does. This one is linear proportional to r to the first power. 2 different ways of saying the same thing. We're going to use the 6 degrees of freedom IMU in this device to measure the angular velocity and the radial acceleration. The sensor board in this device has a 6 degree of freedom IMU, inertial measurement units, and it has 3 degrees of linear acceleration and 3 degrees of angular velocity. So it has a x, a y, and a z. Those are the 3 degrees of spatial acceleration. And it has omega pitch, omega roll, and omega yaw. So we're going to measure this from the accelerometer and this from the gyro. You'll need to know how to convert this value for the measurement tool down here. The IMU, omega IMU, is in degrees per second. We need to have omega in radians per second, so you need to know how to convert that. If I take one complete circle has 360 degrees, and that's the same as 2 pi radians. So we want to convert degrees to radians. So this is 360 degrees divided by 6.28 radians. Okay, so that's 57 degrees per radian. So 1 radian equals 0.3 degrees. So we're going to divide the gyroscope number by 57.3 to get omega in radians per second. The accelerometer gives us acceleration in units of g's, 1g, 2g, and so on. So to convert g to meters per second squared, we multiply by 9.81. But actually we want to express it in terms of centimeters per second squared, because that will give us a nice number here to fit to the data. So we're going to say that a radial in centimeters per second squared is 9.81, no, 981 times a in units of g. Okay? Because then if we do it that way, if we plot a radial as a function of omega, we get a nice quadratic fit here, and we'll do a polynomial fit, and the shape of that curve then will give us a value of r in centimeters, and you're going to find that you get very good results. So that's the story of what we're going to do. We're going to take an object, we're going to embed it in a little centrifuge tube here, the cardboard tube that you have, spin it around in a circle, spin it around and around and around, vary the speed, and take measurements of acceleration versus omega. How many measurements are you going to do? So people always ask me that. How many data points do we take? And I always say, well, more than 3 and less than 1,000. So it's a joke, right? So I'm going to tell you, I want you to take about 200 to 300 data points. And you're going to say, whoa, that'll take us forever, okay? Now, it'll take you about 20 seconds to take 300 data points, because the IMU spits out data at 10 hertz. So every 10th of a second we get an omega and a reading, and the computer will take care of plotting all that data up. Here's the centrifuge you're going to use to spin the sensor in a circle. 2 loops of string, one to hold in your hand, one to wrap around your foot, so you can string this out and hold it in tension, wind up the string, and let the string unwind to spin it around in a very nice controlled way. IMU sitting in the sensor board here, counterweights here to make this thing spin in a balanced sort of way. We want to make sure you mount this board here with the USB port. There's the USB port directly on a line perpendicular to the axis of rotation. So here's the Bluetooth antenna, here's the USB port. The IMU is the little black dot right there. That's where we're going to measure to. So for this, the way this is set up now, the distance from the center of rotation, which is right here, to that little black dot, black rectangle, is about 12.7 centimeters. That's the value. That's about the biggest value of R we can use here. The orientation of the pitch, roll, and yaw, and AX, AY, and Z is in a figure in the book here. This will be a fancier photograph when I get the final version done. But here's the X, Y, and Z axis for the acceleration. So acceleration in the X axis, in the Y axis, or in the Z axis here. That's AX, AY, and AZ. The gyroscope measures roll, pitch, and yaw. So here's the yaw, here's the roll axis around the y-axis. So that measures the angle of rotation along this axis. The pitch angle, which is the one we're going to use, is along the x-axis. So that's pitching this way up and down. And here's the yaw axis along this axis here. So if I go like that. We're going to mount this thing this way on the centrifuge. So we're going to be measuring the acceleration. The radial acceleration will be in the y direction that way. And the sensor is going to spin around this axis. So we'll be measuring the pitch axis on the gyroscope. Let's build a centrifuge. You need 2 about 6-foot lengths of string. I told you originally that you needed about $1 worth of quarters. We don't need that. We don't need the plastic cupping. We'll get rid of that set of plastic cups. And we really only need about 2 quarters in this new design. So first of all, let's find the center, mark the center of the axis of rotation. So take a straight edge, your ruler, line it up on the center of the alternate pair of holes like that. Draw a straight line between them there, and a straight line between these two guys here, right through the center. The center where those two lines intersect then is the center of the axis, the radial axis along which we're going to put the accelerometer sitting here like this. I told you originally that you needed about $1 worth of quarters in a plastic cup to hold them. We don't need nearly that many. We don't even need the cup. We just need 2 quarters for the counterweights. So we'll put those there. The accelerometer goes in the plastic cup with the battery side facing up. Okay, battery side facing up like that, so that when you turn the top over, you see the accelerometer block and the LED light sitting there. So put this in with the battery side up, and you can put the lid on, but I've discovered that if you put a couple of square pieces of paper just to hold a little pressure there against it, it has a tendency otherwise to wobble around. So put the put the paper spacer on there, and now it's locked in there nice and tight. Okay. So we'll mount this on here in a second. We've got this on here. So take the 2 loops of string, about the same as your height, and loop them through on both sides. One on this side, into here, and into here. So pull the 2 ends of the string together to even them out. Okay. So now you have the device looking like this. Okay. The ends of the string together, and we want to make this a kind of a nice stable platform here. So take the device like this, and about 4 inches from this line to here, tie a knot right there, just to make this a nice, well-defined fulcrum pivot point. Pull that through like that, make a knot there, and then this way you can adjust the level angle like that to make it level nicely. Do exactly the same operation on the other side. Oh, before you're done then, we want to turn this into loop. So the final end, tie that into a knot here like this and down here. So pull the 2 ends together. Now we've got the same loop on the other side. Pull them together, and again about 3 to 4 inches on this side here, tie a knot, a single knot in the double string pair there, about like this. And a little bit closer like that, that's fine there. And then again, at the end of this, tie this together, so now we have a full loop. So, there's that. We want to mount the accelerometer and the gyroscope. We want to mount the IMU board. To do that, you need to be careful of one thing only. You want to mount it with the big flat side sitting down. Okay, that means you can see the accelerometer and the LED there. You want to pay attention to where the USB port is, because the accelerometer is the tiny little black rectangle sitting right there, just to the right, as I look at it from the LED. On the line between the center of the board and that USB port is where the accelerometer was. And we want that axis to line up with the axis of the board. Okay, so take your accelerometer, and let's do it for the furthest R we can get, which is to place this about here. Take a big long piece of Scotch tape, okay, and tape it roughly centered up and down on the board like that, sitting here. Tape it there, make sure it's lined up along that axis. Tape it there like that, tape it around, and maybe one more piece of tape to hold it in place there like that, and that mounts the accelerometer. Take 2 quarters, and for this furthest distance here, it turns out 2 quarters sitting about like that is just about right to balance this. Get that string out of the way. Tape this here like this, tape it around the bottom, tape it around that way, maybe another piece of tape crosswise to hold it. This has turned out not to be so critical actually for balance, so you may not have to move these very much. So there's a finished centrifuge. Let me bend this up so you can see how we do this here. So you're going to put one end of the loop just around your hand. You may want to wrap it around a couple of times depending on how tall you are compared to a standard 2-meter man, a 6-foot man. Put the other end of the loop around the bottom of your foot like that. Okay. And now you can wind this up. Okay. You can wind this up to store energy in the spring, which is this string. Okay. And there are 2 ways you can wind it up. This way or this way. It doesn't matter because we're going to take the square of the angular velocity, but it's a little nicer if the curve looks positive going up. So I want to wind this up this way by pulling the right-hand side of the accelerometer toward me a number of times like this. Okay. Number of times like that. And if I wind this 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, about 40 turns gives you a nice speed maximum. Okay. So it's ready to go now. If I let this go, it'll start spinning up. But let me actually take some data here while we're doing this. So I'm going to lean this against my foot, come over here to Sphero, the Sphero app, and take some data. So I pull down Programs, Create, and create a null program, Canvas Loading, and I want to start it. It'll find the board. It's this one here. I click on that and it'll light up the LED here once it's found the board. So it's found it now. So I can take some data. So it's unwinding, slowing down a little bit, slowing down, almost going to 0, and it'll swing back a little bit. It'll overshoot and rewind a little bit. Not very much, probably, just a little bit there. Get a little data there, actually. Okay, so stop there. Stop this. So now let's look at that data set and see what it looks like. I come over here to the 3 dots on the upper right-hand corner, pull that down and pull down to sensor data. And what do I see? I see only 2 things that are relevant, the gyroscope and the accelerometer. Location, orientation, velocity, and distance depend on the other sensors in the device. So this is silly. This orientation is kind of okay. The velocity makes no sense. The distance makes no sense. The gyroscope does, though, because here's the gyroscope data. This is theta dot, d theta dt in degrees per second, and it goes up to 1500 degrees here for this value of twist that I put in. The maximum value of this is 2000. If I went faster than 2000, I'd get a flat top up here, and I got to either throw that data away or start over again. So I come down here, and the only thing I care about is the pitch angle, so I can get rid of the roll and the yaw. It's just this green curve that I care about. I'll pull this slider over to the right to see the entire time history of omega versus time. Okay, here's where I started it. Peak there at about 1500, went down to 0, overshot a little bit like that. So there's the gyroscope data for the pitch angle. Let's see what the accelerometer data gives me for this run that I just did. Here's the accelerometer. And again, I only care about the y value of the acceleration. I don't care about the x. I don't care about the z. I don't care about the total. Okay. The only one I care about is this purple one, the y. And this now is the whole time history of the accelerometer data. And if you look very carefully, actually this barely started to flat top at 8 Gs. 8 Gs is the maximum acceleration that the accelerometer can read. So we should have slowed down, but this will be a good data set to look at, though. So that shows you how to build the centrifuge and how to take the first data set. Now, in the next section, we'll start looking at how to analyze this data using Excel and plot radial acceleration versus angular velocity. Now I'm going to show you how to analyze that data set you took. So we've got the gyroscope data here and the accelerometer data here, but we want to get the actual numbers because each one of these clicks here is a data point set. So I want to download the CSV data sitting there, and I'm going to call it something. I'm going to call it R equals, and I'm going to measure now. I forgot to measure it when I did that last thing. I'm going to measure the distance from the center of the axis to the rotation point. The center of that from the axis of rotation is, put the zero, remember, careful, this ruler has a zero offset. From there to the accelerometer chip is about 12.7 centimeters. So I'm going to call this file R equals 12.7. I hope it'll be okay. It may not get confused about that. Yeah, it'll be okay. So there's that data set. And now I'm going to look in where I keep those things. And here's that file. And that file is an Excel spreadsheet. Let me pull this up here. And this has a whole bunch of data that we don't want. So now we're going to get rid of everything except the time column, the acceleration in the y direction, and the pitch d theta dt. So come up to the Excel spreadsheet and highlight columns M through S and edit, delete them away. Then delete H through K, get rid of those. And then delete B through F, edit, delete those away. And then we're left with three columns. These three columns here: time axis, the time variable, the gyroscope pitch angle, and the accelerometer y value. So we don't really care about the time so much, except that if you want to peel off some of that early data, you can. We can just leave it there. I want to plot now. I want to plot the accelerometer data versus omega, but I'd like to go ahead and convert it to the proper units. So first I'm going to convert the gyroscope omega to, instead of degrees per second, radians per second. So I'll enter a column here that says omega in radians per second. So I'm going to get that number by taking the gyroscope pitch rate. So I'm going to say that this value is equal to, I use a formula, or I simply say equals. Okay, so it puts an equal there, and it's going to be this number here, the gyroscope pitch angle, which is B2. I need to convert degrees per second to radians per second, so I divide by 57.3, and that gives me that number. I'm going to take that number, I'm going to copy it, edit, copy, and paste it in all these other numbers down here all the way to the end. There's the end of the data. And I'm going to say edit, paste. So that takes that equation, the conversion factor from degrees per second to radians, and puts it there. Now I want to convert the accelerometer data from units of G to units of meters per second. Well, actually, I want to do it in centimeters per second. So this is going to be the acceleration, radial acceleration. And I want that to be in, not in values of G, but I want it to be in centimeters per second squared. That's a nicer number because then the curve fit will give me the number that's in centimeters to give me a comparison with the radius. So this is the accelerometer data, this one here, times 981 centimeters per second squared. That's that value there. I'm going to copy that, edit, copy, and pull it all the way down to, again, to the end of the columns. So here are all these nice data sets that's sitting there, and I'm going to edit to paste that equation in everywhere. So now I've got omega in radians per second and acceleration in the radial direction, centimeters per second squared. Let's plot those two data points. I'm going to go here, highlight those two columns. I'm going to insert a chart. It's going to be an XY scatter plot chart. Okay, and look at that. Whoa, hot dog. There's the radial acceleration in centimeters per second squared, radial acceleration in terms of the omega value, the omega, and you see what it looks like. It's a nice squared value kind of thing. I'm going to click on one of these data points here, and then that'll bring up add chart element over here on the left. I'm going to add a chart element, which is a trend line, and it's going to be none of these things here. I want to do a power law fit, so I'm at more trend line options, and I want to pick on a polynomial fit, which is that one there. There's the polynomial fit. Down here in the bottom, very second to the bottom, I want to look at the equation for that fit sitting there, and I can just barely see it. Okay, so I'll click on that, come over here to home, and change the font size from 9 points to 18 points, and now I can see that. So look at that. Boy, that's almost cheatingly good agreement. I said this was like 12.5 centimeters. Here is y. The y-axis is the acceleration. Omega is, x is omega, and omega squared there. So this is r times omega squared. So it says the value of r is 12.6 centimeters. And that's within a few percent of the value we measured from the center of the accelerometer chip sitting here to the center of rotation. So that's how you do it. Okay. Now, what you could do here. So let's save this file. Save this as 12.7. Honestly, ladies and gentlemen, I didn't cheat. I measured 12.7, and it says that this is 12.62. That's better than me. Do I want to save it? No, I want to save it as an Excel file. So I'm going to save this as, that kind of file there, and save it that way. Now, I'm going to save it with that same r equals 12.7 value. If you're savvy with Excel, you could also save this as a template and use this same process over and over again. If you're going to be doing lots of these things, maybe you want to do that. I have a feeling you're going to end up doing only maybe 3 or 4 different radii. It might be easier for you just to go through this whole process all over again. I'll put some notes in the document to tell you how to do that. Anyway, that's how it works. Look, you get a beautiful fit to all these data points here in very good agreement with the radius. So start measuring some a radial versus omega squared values. Adios.